I'm going to try and take you through Africube, which is I would say the follow-up on Klitschko's. So I'll take you through what we've done, and hopefully show you where we are at the moment. So this is sort of a starting point where we've got the frame design done. We've got the receiver board, the transmitter board, onboard computer is done. We've got some issues on onboard computer. There will probably be another version of that. Magnetic stabilization board, battery board, that's done. Electronic power supply unit, that includes the power management of the MPPT controllers, and antenna deployment part of all sits in there, that's done. And then a sensor board. So we don't have space at the moment for the sensor board, but we're probably going to combine the transmitter and receiver board on one board, and then we'll have a proper experimental board for additional payload. So that's the status at the moment. So what must our satellite do? So I've got a list of stuff that we need to do. It must have a linear transponder. It must have a bandwidth of 20 to 30 kilohertz. And in fact, we at the moment are testing with 40 kilohertz, and it works pretty well. Must be able to receive upload on 70 centimeters. The input of the receiver must be equipped with a narrowband low loss filter to prevent the transponder being interfered. Okay, that's all done, part of the design. Must be able to transmit on 145.865. Total gain must be 121. And I think we're exceeding that gain at the moment. We have to have an NDS of about minus 110 dBm. We're about there. Maximum output power. At the moment, we're sitting at 220 milliwatts. The new board is possibly pushing about 550, but we're probably going to run in between there, probably about 300 to 400 milliwatts when we actually gonna put it into space. All harmonics and spirits must be below that. We've tested, that's fine. The 2-meter output IMD at 100 milliwatt signal must be less than 30 dBc. I think that's fine. Automatic gain control. In fact, we've got a 60 dB gain control capability on board at the moment. The value of the AGC control signals must be provided to control all services as RSI for telemetry purposes. So what I'm going to take you through later on is how we're going to control AGC and some of these settings which we can probably control from ground if we see that the default optimum is not perfect, and we can apply some of those things. We can, in the past, the settings was that we actually going to read the values of the analog circuits in the Klitschko's, because now it's totally digital system. We're actually reading it off the IQ values of the SDR itself. The transmitter must comply with the satellite common interface specifications, which is the PC104 plug. So we're still doing that. Parts of it is not using that, but it's to save space. That PC104 connector is quite big, and we sometimes run out of space. Okay, so the transponder must be non-inverting, so that's definitely what we've done. It must be possible to switch the PA on and off. That can be done. Directional coupler must be used on the output to provide forward power and reverse power readings to the controller. That we do not have at the moment, but we do monitor the IQ just before it goes out to the actual transmitter path. So we do actually have feedback, and that feedback is used as part of the AGC, and we also can use that with some code to, I would say, optimize the AGC so that if we have areas in the world which is very noisy, it will automatically increase the AGC or decrease the AGC as required. But that delay of the noise level is the part that we need to still define. Typical output power levels must be adjusted. That we can do from ground as well. All SMA connectors, that's done. A power supply to be transformed will be 5 volt regulated. So at the moment we're using 3.3 and 5 volts. The onboard computer is majority 3.3 volts. The maximum power consumption should be less than 1.5 watt. So what we did is the original design, because it used, Kletsco's used a lot of analog circuits, we've now implemented a lot of the analog stuff in the DSP signal processing. So what we actually are winning by doing this is by using the default power consumption of the onboard computer, now actually implementing analog circuits or implementing analog circuits current, let me put it differently. What the analog circuits would have used power for is now being used in the actual onboard computer, so we're not using more power, but we're using actually less. So we actually right around that budget area. Test that we've done is, I think we're okay. 2 meter telemetry transmitter, possibly the ADF7021. That was the thinking on Kletsco's. We now actually all use DSP, all digital signal processing. I'll show you some details further down. Format of telemetry is AX25, and we're thinking of even other telemetry technologies as well. I'll show you that. 70 centimeter command receive will be fed from the same input as the transponder. That was quite important. The tests that I've done now so far is we can do command control without affecting the transponder. So the transponder can operate and we can control it, so we don't have to switch the transponder off to control it. So that's still in a testing phase now, but so far it looks very good. Telemetry command communication between transponder and controller will be I2C. That's all done. It's all internal into the onboard computer, so we don't really use much I2C anymore, except for antenna deployment and solar panel current monitoring. That's the only place we use I2C at the moment. And we must be able to switch most components on and off on a satellite, and obviously control the power amplification. Telemetry must be continuous. What we're going to transmit, it could mostly on mode 0 would be CW and all other systems off. And if we in the other modes, it's combination of slow scan TV, APRS, LoRa, and even more modulations which we're thinking of, but for now that's what we're going to transmit. The working stuff at the moment, CW, slow scan TV and AFSK. Frequency at the bottom edge of the transponder. So we want to put the beacon at the bottom, and I'll explain to you why later. The IPRS might enable, might also have GPS. I don't think so. I don't think we have space for it, but we'll see. If we can get a GPS that could use very low current, we might be able to add it, but I don't think we should be, we're going to probably have space for it. And the CW details we'll publish later on, once we get to the final stage. So here's a little picture of how the satellite internals work. We've got experimental data, we've got APRS beacon data, and control reply data. Basically, that's the top 3 blue blocks at the top. And then we use Direwolf libraries to create AFSK for us. That goes into the GNU radio block, which basically modulates that with FM, and that gets transmitted out through the adder block into the RF output stage out as a beacon. So all those inputs are used to create the beacon. Then on the left, just below, you'll see that the little brownish block, that's your transponder input. Now there's 2 inputs there. There's the actual transponder and control. So what happens here is the actual SDR part gets forwarded and disseminated to 30 to give us another 12 dB gain on signal to noise ratios, which is really good. So we've got a very good sensitive receiver. We can do 80 kHz low pass filter just to limit our bandwidth on the output, and then we've got a rational resampler to take it up to about 480 kHz out to the actual RF stage. Then the AF output of, we've also got a narrowband FM receiver which runs parallel to the SDR linear block for the transponder, and that's your command unit. So that will always stay on, and that always has to stay on because we need to control the satellite, and that will send all the audio, demodulated audio to Direwolf, which will then write all the control data to the control commands, and that gets picked up by the mode monitoring system, which I'll explain later. So this is the front end. So this is the front end board, the picture on the left there. So we've got 435 SAW filter in the front end. We've got a preamp stage, another SAW filter, RF receiver, IQ, phase shift, and analog AGC unit. And then we've got a 12-bit A to D converter. I can convert up to 10 megs. We're going to run it at 6 megs. And decimate it to 25 to give us that 12 dB additional noise floor, which you can see on the right hand side. The top signal is without coming in, and the bottom one is after decimation. Therefore, we are winning that 12 dBs there. So this is the RF output stage. On the left, you can see we've got a output filter, bandpass filter. We've got a second RF stage, first RF stage, impedance matching circuit, and that goes to the onboard computer. Here's the transponder signal, basically showing you, and the beacon. So the beacon, when I did this, was on the top. It's now moved to the bottom. And the reason for that is that if you're using a dual frequency radio and you link the two local oscillators with the same shift, it would be quite nice, because if you think of it, if your Doppler sits at the bottom and it goes up and you need to increase the frequency even manually through a radio, it makes sense to put the beacon at the bottom. You can listen to the beacon and then you can just jump up as the actual satellite comes over you. So I think that's the reason why we're moving it to the bottom. It will make sense and make communication better. This is the EPS, electronic power supply unit. So basically we've got some logic inside it, and this is the first logic that will operate when the satellite gets deployed. So there's a separation switch, which is a little switch, micro switch, that sits on the side of the satellite. If it gets pushed out of the pot into space, that little switch will open, and then will give power to the onboard computer. There's also an additional switch below it. That switch gets switched on when they actually put the unit in the pot, so that the satellite is always off until it's put in the pot, and then it will wait for the second switch to open as it get pushed out of the pot. So there's the two switches that we had to design in there. The EPS unit also then has 12 MPPT controllers to maximize power charging onto the battery. We've also got a special electronic battery disconnect capability, so that if the battery goes short circuit, we can still operate the satellite, or let's say the battery is open circuit, doesn't matter. Then we can still operate the satellite when it's in sun. So that's why we've got the switch here at the bottom. This one here. Then we've got another part that I didn't actually put in a picture here, is the antenna deployment unit. So that's a little fuse wire that a little fish line or nylon plastic thread gets wound around it. And once we're ready for deployment, and that's normally about 5 minutes, if I remember correct, after the actual unit is being pushed out of the pot, out of either the rocket or for International Space Station. Then that will burn the little wire, and the antennas will deploy. This satellite of ours has also got two little doors. That's got additional solar panels. Then those doors will also open, and we have the additional power for that. So this is the onboard, the electronic power supply unit. So the connector at the top is got the 12 solar panels that is connected to it. Then we've got 12 current sensors. So we will be independently be able to measure the current of every solar panel, and that's more than one purpose. We want to know if the satellite is stable or is it still rotating in space. So that will give us feedback. If the if the satellite rotates, then obviously those signals will obviously go up and down. We can also then find out if is the orientation correct, is the right panel showing to the sun in relation to Earth, and so on and so on. Then we've got a 16 channel 12-bit A2D on there to read the actual power from the solar panels and the actual charging current, and so on and so on. We've got a 3.3 volt A2D regulator, and that is specifically for the A2D converter, that 3.3 volts, sorry. Then the 2x dual PFETs is there to control the actual antenna deployment and to disable the battery connection. So we've got those two on there. We've got a 5 volt regulator. We've got a 3 amp current source regulator, which is the antenna deploy. That is going to melt the little nylon unit to deploy antennas. We've got FET enabled charger, 3 volt regulator. The pod switch is connected there. Antenna deployment burns the fish line. That's the connection there at the bottom here. And then umbilical cord. So that is the actual connection on the outside, which will disconnect the switch so that this circuit can be activated with a second switch. And this is the charge controller. It's quite intelligent. It's got a lot of logic in it. It will calculate how much charge we have in the battery, and so on and so on. And then there's two LEDs, which you probably won't populate on the space unit, but it's for testing only. So this is just another block diagram of sort of explaining how it operates. So we've got the solar panels, kill switches, battery charger unit, 3 volt and 5 volt regulator, and a power distribution board. That's all done on the electronic power supply unit, and the A2D converters is read through I2C from the onboard computer. So this is sort of, if you look at how the unit is divided into different areas. So we've got the power supply units, which is basically the panels, onboard computer, and the magnetic stabilization board. So on the magnetic stabilization board, there is magnets, permanent magnets, and there's space inside the permanent magnets for the battery, and that's where it's going to be mounted. That must also be in the middle of the satellite, so orientation can be controlled quite well. RF receiver board, that I've showed you roughly. The CPU unit, which is onboard computer, filters, output, and then the sensor board, which we still have to make space for, and the antenna deployment unit. So that's sort of the parts that the whole satellite consists of. This is the onboard computer. So we're using the Raspberry Pi compute module. We're using the version Pi 3, and there's a specific reason we're using the Pi 3. It's low in power in comparison with the Pi 4. It's got enough processing power for our DSP signal processing for the SDR capabilities that we have. Obviously, the more the better, but because of the power constraint, this is the unit. It is hardened for space, so that's the reason. Secondary reason we choose this device. The unit below it, this board around it, is the board that we've developed. which basically has got a Raspberry Pi connector and a PCI-1.4 connector. And this was purely done for testing purposes, this part, so we can use standard devices, plug in and test certain aspects. We've got a audio coming out, umbilical cord, so that we can control the unit if it's still built in its satellite frame. There's a little opening, we can still plug our computers in there and we can monitor it there. It's got a built-in SD card, and we're going to use that to have another copy of the operating system. If the first one failed, it could probably boot from the second one. It will also store all the statistics of the sensor boards in this unit. This compute node has got its own flash internally as well, so we're going to store the operating system there. But if that somehow get corrupt, we can read it from here, if that's still possible at that stage. We've got the real-time clock and the battery here. So here's the real-time clock chip and the battery for it. This is a watchdog. For the guys that don't know what the watchdog is, it will monitor the software. And in the software, we have to tell a watchdog we're alive, we're alive, we're alive all the time. And if it doesn't get a message for that we're alive, then it will reset the operating system and we'll start from scratch. This is a boot select capability. I don't know, this arrow is showing the wrong point and show here, but basically we can either boot from the SD card or internally. So by default, we will always start boot internally, and then SD card is only for testing purpose. RX interface connector, that's our RX interface, and this is a PC104 connector at the bottom for the rest of the circuit. So I'm going to take you through some of how we're going to control a satellite. So this is how the software will control. This looks a bit hair-raising, but it's not that bad. It's about 13 modes, and we're probably going to use only a few of them, probably 3 or 4 if a satellite works fine. The others are more just to adjust the satellite and do small control capabilities. So in the beginning, the system will start up when the micro switch is released out of the pot after 5 minutes. Deploy the antennas, which is this part here. After 5 minutes, deploy the antennas, and then we'll go into mode 0. Mode 0 is basically satellite on and CW mode. So we will just enable a CW mode and a control so that we can still control it. And then after it's got all kind of mode capabilities which we can control. And yes, sort of high level what we can do. So 0 is CW only mode. Mode 1 is CW and transponder on. Mode 2 is enabling slow scan TV, and we can then select to send an image from the onboard SD card or from the camera. We plan to add a camera onto the unit. We're not sure if we're going to have space. We're looking at now maybe putting it between the antennas, but we will see once we get closer to the antenna deployment being completed. Mode 3 is we've got a text-to-speech capability, so we can upload text to the satellite and it can talk out speech, and that could be used in special events, for instance, at a school or a university having a special event. And we can switch it on with the transponder because it will be transmitted on the beacon frequency, the speech, and the transponder can still operate on its own. That's why we've got mode 4 with transponder. That also depends if we've got enough power to run both. Mode 5 is enable slow scan TV beacon with transponders as well. Mode 6 is APRS command mode only. That's if we realize that something is going wrong on the satellite. We will put it in mode 6, which will then only allows us to control it, and it will not do anything else but listen for commands from us, and it will send an APRS beacon. Mode 7 is text to speech, and this one will allow us to enable other features as well. We can combine CW, we can combine slow scan TV, so we can maybe make it so it rotates between the different modes. That's probably depending on how much power we're going to have. Mode 8 is reset the satellite totally. Let's say we've got some upset with some configuration. We can send a command to it to reset all configuration to default. And mode 9 and 10 is reload operating system from SD card to cache. So that is sort of really if we've got something that's been upset in the normal operations of the satellite, but we can still control it. Then we'll use command 9 and 10 for that. Mode 11, configure payload sensors. So depending on what payload we can have on, we have got with the universities, some of the universities we're going to have some sensoring equipment on board, and then we can switch the sensors on and off and send the data down. Mode 12 and 13, load program and run program. So what we thinking of doing, and that's the part that I still need to test, is to upload scripts from ground and then allow us to run the scripts, and that could put the satellite in sequential modes and configurations and so on and so on. So that's stuff that we still want to try and test. There is a couple of other modes that we've added to control specific configurations in the satellite, for instance, AGC, output power levels, and so on and so on. So there's a few other modes which I think is not that important. So just to take you through, for instance, what is involved in getting a beacon running. So we basically check if the beacon, if we have to push it into mode 0, what is the beacon power level? What must be set it at? What is the beacon, CW beacon message that we need to send? And normally 90% of the time it will send a power level and a reset count of the satellite. And obviously it's ID and a small message. So that, and then it will, there's also how often does it need to send it a CW message, and that's the interval that we need to configure. Mode 1, CW beacon and transponder, so that's very similar. So on the transponder side, we need to check the transponder power levels, the AGC level, and that will continuously be checked in a certain interval to adjust the levels automatically. Then on your mode 2 CCTV, that's very similar to transponder. We will check the power level and then check the regular interval. How often do we send the CCTV image? Do we send it continuously? Do we send it every 2 minutes, every 5 minutes? Do we send different images? Do we send the camera? Do we send the file on the SD card? That's all the configuration that's involved there. Mode 3, text to voice message. So we're going to send the text up to the satellite, and then we'll probably have a couple of predefined messages in the satellite itself, which we can then select. And the vocoder, the speech vocoder, will then play it out on the beacon, and then that can will be added with a CW ID just in between as well, so that at least we can identify the satellite. Mode 4, the text to voice with transponder. Basically, that I've just told you the two different options. Mode 5, CCTV with transponder, same story. So the intervals at the power levels we're going to combine, and then the transponder level will operate on its own. So each of these blocks on the right hand side is a thread on their own, so they operate independently from each other. So they don't need to wait for each other to do things. They can manage the one thread will manage the transponder, and the other thread will manage the CCTV. Enable APS beacon with command mode. So this is where we will mostly control the satellite, where we will receive commands to put the satellite on different modes, to upload configuration data, to tell it what to do, and so on and so on. We've got a special command 7 where we can configure the satellite a custom configuration, which is not the default mode configuration. So if there's a reason we want to maybe combine slow scan TV with speech. We can do it, and that could be operated simultaneously. So this is the command that will do that. Mode 8 is that reset. So on a reset, we can reset all the configuration. And then basically it will go and read the default values from the SD card, rewrite it into the internal flash memory, and will go back into mode 0, which is OCW only. And then we can probably gonna send it a command to say, give us back all the configuration, and if that all looks correct, then we'll put it back into mode 1, which is transponder, or whatever mode we want to put it in. So that's really something, just in case we've got some configuration that's corrupt, we will probably use this command. Mode 9 is load operating system from SD card. This is really something that we don't want to do. This is really only if the satellite's normal operating system has got corrupted, but we can possibly still control it somehow. Then we can ask it to copy the backup operating system from the SD card into the internal flash and reboot. So this will probably happen in 2 stages. We will let it go and calculate the checksum of the backup version. Then load it into flash, do a checksum again, and we'll then send those 2 checksums to the ground station. If the 2 checksums correspond, then we will send another command after that. You'll see that is the next one. It's mode 10. We will say, okay, go ahead. We've done the checksums on Earth. We're happy with it. It's correct. And then we'll say, okay, load it and reboot. And then we pray that the satellite will come back up. That's really a last resort. Mode 11 is sensor monitoring. So we can, depending on what universities decide on what sensors they put on, we probably might have to sometimes configure the sensors to do certain things, and the interval, how often do we need to read the data for them and store it on the SD card. So all that configuration will be done in mode 11. Most of the data will be sent down to Earth on APRS because it's a lot of data. And I don't think we can send it down to Earth any other way. So all sensor data will always be sent down through APRS. Mode 12, upload program and save program. So this is the thinking here was that we could write little batch sequence programs, upload it, and we can let then this batch sequence control the different modes. For instance, if we want a special day that we want maybe the first 30 minutes to run slow scan TV, next 30 minutes voice coder, next 30 minutes something else, but it's another side of the world, we can then load this program and it will schedule for that time and kick off and put the satellite in that mode. That's the purpose of what we plan to use mode 12 for. This is basically just running. The first one is loading the program, 12, and 13 is actually executing the program. This is 14. I don't know why I've got here 12, but I probably copied and pasted. Enable APRS in command mode. This is where we reboot a computer. So let's say, for instance, we do find there's something corrupt or something is not operating optimally. We probably can try and reload the default configuration, maybe do a couple of adjustments. If that doesn't work, we can reboot the computer. If rebooting the computer doesn't work, then obviously last resort is to load the operating system from the SD card. So I think that's probably the ways we try and recover the satellite. This is sort of the satellite band plan. Why 80 kilohertz? I think it's our power limit. If we obviously can be piggybacked on another satellite where we can have a lot of power, I've done tests, we can even do 120 kilohertz easy, even more. In fact, I've done tests with 240 kilohertz, but it's the output power that we will have to up a bit. Then we'll have to just add a new RF output stage, so we can actually build quite a wide transponder if we've got a lot of power. Why beacon at the bottom? I've explained earlier, if we use a Doppler approach where we have the A and B local oscillators of your radio linked, it's easier to operate the satellite by just upping the frequency from the beacon upwards, and the receiver will then follow. Ground station. Okay, so how do we build a ground station first? We can use the open source SatNox system. They've got already AFSK decoders, demodulators that we're going to use by default. So if you just look in the world, they're all over the world. So we should be able to get all our ground station data free of charge, all recorded and put into a central database, and which we can then analyze and use. So they're already monitoring 618 satellites. They're using 48 modes. They already listening to 1,186 different transmitters. Of those transmitters, 84% of them is basically active. They've already recorded 111 million data points of all the satellites. So it's quite an effective ground station capability. Frequency bands covering UHF, VHF, S, X, and L, so which is quite a nice capability. So I think I'm going to try and get this up and running for our Africube shortly, so we can start pushing test data into SatNox, so we can actually see that it records our data. And then if that works, then they will probably enable it for the whole world. So once the satellite's in space, then obviously whoever schedules recording will then send the data to us automatically. So this is how SatNox works. It basically got the spectrum view scheduler, and it will schedule your satellite reception, and it will record the spectrum view that you see on the middle to this blue section here, which is quite nice. It also records the audio for you, which is quite nice, so you can play back your audio back that was recorded, and then it also actually decodes the data for you and put it in a database, so you can use that data to extract your battery voltages, your sensors, your reset count, your satellite mode details, whatever you've sent down to Earth will then be in a database, and you can analyze that. They've got custom reports that you can build on the ground station capability, so you can write your own reports, for instance, and show your battery voltages or whatever you're interested in. I just took some examples here. Why I'm saying we probably can get the camera on board is this is I think University of Surrey has put this little Raspberry Pi Zero in space, and they've put this lens here and mounted here below this little Raspberry Pi Zero. There's a little connector going down, and I'll show you the actual picture. Let me just copy this. I'm going to show you a video as well. This is sort of a picture that they got from space from their little Raspberry Pi. It's not a bad picture. I would, coming from a little Raspberry Pi cam, I was really impressed. So I think that's what we're aiming for. If we've got space between the actual antenna deployment parts, that we can put this little camera in there. It's actually very small, the camera. It's just a matter of the actual antenna deployment part is twisting, and our cables will have to twist with it. Let me see if I can get this video to, yeah. I don't know, Hans, how are we with time? Can I play the video still, or are we short with time?
We're short of time. You're over time now. If the video is
Okay.
short, just maybe show it a little bit and then cut if it's too long.
Yeah, let me try that quickly. I think I've got it open on my browser. Can you see the video?
Yes.
It will probably start showing now.
Okay.
So you can see the little cable on the right-hand side that went over the lens there. But yeah, it's not bad for a little Raspberry Pi camera. So I think that's probably what we would be able to get from the satellite. I think that's it from me. Thanks very much.